values of characters, here you consider all the characters of this form, but here you do not consider all the possible rational alphas. Here, alpha ranges in the set. Zero, 1 over n, 2 over n. Or in other words, this alpha should be between 0 and 1, and if you multiply alpha by the integer n, it must be an integer. So in other words, here, we do not consider all the possible alphas. We only consider those alpha, which if you multiply n, you get an integer. Because n is a factor of this q minus 1, so you really consider a subset of those alphas. So this is true for this ui non-zero, because here I only define the characters on the multiplicative group of fq. So this is an equality for all ui, for all non-zero units. But if you want to make the equality still to be true when ui to be 0, then you need to make the following convention. So you still need to define the value of these characters as 0. So I require that its value at 0 is 0 if alpha is not an integer. And I define it to be 1 if alpha is an integer. Then under this convention, this equality is also true for ui equals to 0. Okay? So this, the proof of this fact is just a case-by-case proof. Just divide into these 3 cases and check that both sides are equal. So the good thing is we write this number of solutions of some equation as the sum of some characters. So now I can rewrite this number of solutions as the sum of this number of solutions. But for each of these number of solutions, it is the sum of some characters. So here we have alpha 0, alpha 1, alpha r. Then we have chi alpha 0, u0, chi alpha 1, u1, chi alpha r. So the number of solutions of the original homogeneous polynomial become the sum of the product of these characters. So it seems, oh, we make the number more and more complicated. But Andrew Weil has the insight on how to simplify this huge sum. So here, these alphas will satisfy this condition. All the alpha i's are between 0 and 1, and if you multiply, it's a rational number, and if you multiply the integer n to each of these alpha I, you get an integer. So this is the range, this r plus 1 tuple. For this u here is all the r plus 1 tuple, such that this linear function is 0. So this is the range of the sum. And these two sums, the range of these two sums are independent, so we can switch the order of the sum. You can first take the sum for all the alphas. And then you take the sum for all these u's, and then take the sum of these product of characters. Then, in the outer summation, we can divide all these r plus 1 tuple into 3 cases. The first case is all these alpha i's are 0. And then you take the inner summand. And here you have the product of the characters. The second part is some of these alpha i's are 0, but some of them are non-zero. Okay? Then again, we have the inner summand. Finally, you take the sum for all alpha i's such that none of the all the alpha i's are non-zero. Why I divide the sum into 3 parts? Because the first part is very easy to compute. If this alpha I, each of these alpha I is 0, you'll see that this chi 0 u is always equal to 1 for all u. Because this is the it maps a generator to the complex number e to the 2 pi alpha, and when alpha is 0, it is becomes 1. So if all these alpha i's are zeros, then each of these characters becomes 1. Then actually the product becomes 1. Then how many ones do you have here? The number of these ones is equal to the number of solutions of this linear equation. But what is the number of this linear equation? Once you fix the number of u1, u2, ur, if you want to make this linear equation to be 0, then the value of u0 is uniquely determined. On the other hand, there is no more restriction on the value of u1 to ur. So for each of these u1 to ur, they can take values in the finite fields with q elements. So in total, you should have q to the r solutions to this linear equation. In other words, you have q to the r once in the first sum. The second summation is a little bit more complicated, but you can show that the second summation, if some of the alpha i's are 0, some of them are not 0, then this part will give you 0. Then, under this simplification, we see the following. So we see that you can write the number of solutions in a homogeneous equation is q to the r, which corresponds to the first summation, plus the last summation. Here, again, you take the sum for all u such that this linear equation is equal to 0. And then you take the summation with respect to all these alpha i's. Here, all these alpha i's should be between 0 and 1. Here it must be strictly between 0 and 1 because we remove the possibility that alpha I is equal to 0. And also we should keep the restriction n times alpha I is an integer, then we have the last summation. Next, we want to simplify this linear equation a little bit. So I take this ui prime to be this ai times ui. Then, if you do this change of variables, and then you take the summation with respect to these ui's, this ui prime should satisfy the relation is u0 prime plus u1 prime is ur prime. The sum should be 0. And again, here we have the summation for these alphas. And then these characters becomes a little bit complicated. First, we should have some AI inverse, this, and then we have chi alpha 0, 0 prime, chi of r. So under this change of variables, the linear function becomes this. Oh, sorry, I forgot the q to the r, which comes from the first summation. So if you rewrite this huge summation, first you take the summation for all these alpha i's, and then this product only depends on these alpha i's because these a0 to ar, they are fixed numbers. So we have alpha 0, a0 inverse, chi alpha r inverse. And the rest things is the summation with respect to u. And I denote it by S alpha. Here this S alpha is given by take the summation of this product of characters for all these u0 to ur such that the sum of these r plus 1 tuples is 0. Okay? So in other words, this is the thing we want to compute. We show that this number is q to the r plus a summation. If you analyze each of these summands, here, these numbers, they are just some roots of unity. So the absolute value for each of these numbers is 1. Then the resting is this alpha. And this S alpha, this sum is called the Jacobi sum. For the characters chi alpha 0 to chi alpha r. Because if you're this is a sum which depends on the r plus 1 tuple alpha 0 alpha r, and this we define these alpha r's in order to get these characters. So once you have these characters, consider this sum, and this is called the Jacobi sum for the characters of this r plus 1 characters. And to give an estimation of the number of solutions, we need to get an estimation of this so-called Jacobi sum. And here I want to give you an important fact, which tells you that this Jacobi sum is closely related to the Gauss sum we defined at the very beginning. It's S alpha, or sometimes I denote it by J alpha, because it is called a Jacobi sum. So use J. It is 1 over Q times tau 1 0. So you can write this Jacobi sum as the product of some Gauss sum, then you divide by the cardinality number Q. But actually, this is there's an ambiguity, because at the very beginning of today's lecture, I only defined the Gauss sum for characters modulo P. And if Q is equal to P, then we have this equality. All sides are well defined and they are equal. But so this is okay. But if Q is not equal to P, it's the power of the prime P. Actually, there is a generalization of the Gauss sum for characters of a general finite. And in that case, we have a similar result. Each of these Gauss sum should have absolute value square root of Q. Okay, but because I do not have enough time, so I cannot define the Gauss sum for general character for an arbitrary finite. But at least over the prime fields Fp, both sides are well defined, and you can check the relation between the Jacobi sum and the Gauss sum. Then this is pretty good, because we know that the absolute value for each of these Gauss sum has the absolute value is square root Q. So the absolute value for each of these Jacobi sum should be Q to the R minus 1 over 2. So that means this, we have a bound for this term. Then in other words, if I take the difference of the number of solutions of the homogeneous equation to this constant q to the r, it is bounded by some m. Here you need to the Jacobi sum is you take the sum and then you divide it by 1 over q minus 1, then I get the Jacobi sum. Then this, if you divide by q minus 1, you can write it as a product of Gauss sum. So we have an estimation for this difference. It is some number m times q minus 1 times q to the r minus 1 over 2. What is this m? This m is just the number of these r plus 1 tuple. Each of these alpha I should be between 0 and 1. And n times alpha I should be an integer. Of course, there are only finite many such tuples, and the number is a finite number. This m. So here we know that the number of this solution is almost equal to q to the r because the difference is very small compared with this q to the r. So yeah, I think I have to stop here. So in this today I just use this example to show that the relation between the number of solutions to a homogeneous equation with the estimation of the Gauss sum or the Jacobi sum. So tomorrow I will continue with the definition of the zeta function.